Solution dilution. Sounds like the beginning of a poem or something. Let's talk about orange juice. One way to buy orange juice at the grocery store is to buy the frozen concentrate. Why do they sell frozen concentrate, do you think? Does it stay fresh longer than fresh orange juice? Yeah, you can keep that frozen stuff in your freezer for months and months and months, and it's still good. If you have fresh squeezed orange juice and you leave it in your refrigerator, it's a matter of days before it starts to get nasty, right? So one reason is that it lasts longer. Another reason is that it takes up a lot less space. You could also freeze unconcentrated, just regular orange juice, but that's going to take up a lot of space in the freezer, isn't it? And if they're trucking this all over the place, they're hauling all this water back and forth and storing it, and that's expensive. So they take a bunch of the water out of the orange juice and put it in the little can, and then it's concentrated. And it takes up less space, and it's just easier to deal with. Well, the lasting longer business doesn't apply to chemistry, but we do use concentrated solutions in chemistry, and we call them stock solutions, and they're kept in the stock room, right? We have them in stock. And so when we want to make, and in fact, we did this on Wednesday when we did our titration lab. We took a stock solution of sodium hydroxide, and we took 40 milliliters of that, and we diluted it. We added water. Just like if you were making orange juice from concentrate. You take the can of orange juice and you put it in a pitcher and you add water. So we can have in the stock room jugs, bottles of concentrated solutions, and then it's very convenient when we want to go make a more diluted solution because we just take the amount that we need, we dilute it, and we're good, instead of having to figure out what mass to weigh out and getting it to dissolve and doing all that kind of stuff. So we dilute our stock solutions just like you would make orange juice. And there is an equation for this. And it is M1V1 equals M2V2, which looks a lot like, what was that, Boyle's law? P1V1 equals P2V2. But here, the capital M is the molarity, and the capital V is the volume. And just like with the gas laws, it doesn't matter which one's first and which one's second. Your book calls one the concentrated and one the dilute. It doesn't matter. As long as you use one, the subscript 1, for the volume and molarity of one solution, either the concentrated or the dilute, and don't get them mixed up. So let's talk about why this equation works. If you take the molarity, which is moles per liter, and you multiply by the volume in liters, what do you get? You get moles, right? You get the moles of solute. When you take that orange juice concentrate and you put it in the pitcher, you've got a certain amount of orange goodness, right? When you add water to the pitcher, does the amount of orange goodness in the pitcher change? Not unless you spill it, right? You're adding water. You're not adding any orange stuff. You're not taking any orange stuff out. The amount of solute stays the same. You're just changing the concentration and the volume. Does that make sense? You're taking something that was more concentrated, you're adding a solvent and you're diluting it, but the amount of solute is the same. So because there's a point on here we go. Because the molarity times the volume equals the number of moles, and the number of moles doesn't change, then the molarity times the volume of the first solution must equal the molarity times the volume of the second solution, because the moles of solute are the same in both. Couple of notes. This equation applies only to diluting solutions. We do not use this for stoichiometry. I've seen it in some textbooks and lab manuals, and I think there are instructors out there, so I'm talking to the YouTube people. M1V1 equals M2V2. Sometimes people use that to do titration calculations. I really, really do not recommend that, because it will work in some situations, but there are other situations where it will not work. And so I think it's just a very, very bad idea to use that. Use it only when you're diluting solutions. And a lab safety note, when you are diluting acids, we always add the acid to the water. And that's a safety issue. If you add water to a concentrated acid, what happens when you dilute a concentrated acid is it's an exothermic reaction, and it can get very hot. Okay? It can get so hot that it will cause the water to boil. And then things can shoot out and spray all over the place. And in fact, this happened a few years ago at Fresno City College. A student worker had a large, I think it was a large graduated cylinder, and was making a diluting a concentrated sulfuric acid solution. And he made the mistake of putting the concentrated acid into the graduated cylinder and adding the water. And it got really hot, and it shot out like a cannon, and there's concentrated sulfuric acid dripping off the ceiling in the stockroom. It was a big deal. The police came, the fire department, the hazmat team, I think OSHA got involved. It was bad. Now, fortunately, that student was wearing his personal protection. He had a lab coat on and he had his safety glasses on. He still experienced some chemical burns, but they were not serious enough to cause lasting damage. And, of course, it was a huge mess to clean up. And so that's just something that happened a little too close to home. My husband was involved with that because he works there. But that's just something that, you don't want to mess around with. So if you, it just occurred to me, here's one way to think of it so that maybe you can remember, which was it? Do you add acid to water or water to acid? Okay, if you have any experience with swimming pools, you know that sometimes you have to add acid to the swimming pool, right? So the acid is concentrated, the swimming pool is the water, right? You're always adding the acid to the water because you add the acid to the swimming pool. It's never that you add a little bit of water to a swimming pool full of concentrated acid, right? So if that helps you remember. It's just a safety thing. I'm not going to test you on it, but it's potentially dangerous, so it's important. So we should be able to do calculations like this. How much 6 molar sodium nitrate solution should you use to make 0.858 liters of a 1.2 molar sodium nitrate solution? So the first issue is you have to recognize this as a dilution problem. Generally, if they're giving you 2 concentrations of the same solution, here it's both of these are sodium nitrate, and we're given 2 concentrations. And they're asking about making, or if they use the word dilute, that's a big clue. It's a dilution problem. So recognize that this is a dilution problem, and then write the equation for that. So M1 V1 equals M2 V2. So that's kind of our pattern of, we need to find that sort of information. Then let's look at what do we have here. Well, we're given 6.0. Let's not write capital M, let's write moles per liter. Is that a volume or a concentration? Is that V or M? That's M. So that's a molarity. Since that's the first one we came across, let's call it M1. So that's molarity 1. The next number is 0.585 liters. Is that M or V? That's V. Is that the volume of the 6 molar solution? No. So we call the 6 molar solution 1, so then we're going to call this one 2, because this is the other one. And the last number is 1.2 moles per liter. Moles per liter, that's an M, capital M. 1.2 and 0.585 go together. You see that? 0.585 liters of a 1.2 molar. Those go together. This is M2. The question is asking how much 6 molar? How much of M1? So it's asking for V1, isn't it? So V1 is what we're trying to find. Rearrange the equation and then put the numbers in and solve. So we need to divide by M1, so those cancel out and we get V1 on its own on the one side. If we divide one side, we have to divide the other side to keep it equal. So we end up with V1 equals M2 V2 over M1. And so we'll plug these numbers in. M2 was 1.2 moles. That doesn't look like moles. Moles per liter. And volume 2 was 0.585 liters. And that's all divided by 6.0 moles per liter. Check your units. These moles cancel, these liters cancel. Some of the questions, especially in the homework, might have weird units like milliliters. And sometimes they will cancel out, and other times they won't. So just make sure that your units are canceling. Because if your units don't cancel, you probably did something wrong. 1.2 times 0.585 divided by 6. And how many sig figs should this have? 2. So my calculator is giving me 0.117, so I'm going to round that to 0.12, and the liter is the unit. That's the volume. If we're going to make this diluted solution, we'll measure out 0.12 liters of the 6 molar sodium nitrate, and then we'll mix it with enough water to make 0.585 liters. Any questions? This equation has 4 variables, so we'll give you 3 and ask you to find the 4th. Here's just an illustration of making the solution. It's very similar to making a standard solution.